Hi everyone, so today we're going to talk about the mean value theorem. And the mean value theorem basically is similar to the intermediate value theorem, the IVT. This is the MVT, okay, but for derivatives. So just as a heads up, intermediate value theorem, if you remember that was when we guaranteed some function value would happen between two other x values if the function was continuous, excuse me. So now we're going to talk about kind of a similar idea here. If f of x is continuous from a to b and differentiable from open interval of a to b, okay, then there's at least one c value in a of b such that this. Now, this looks a little bit strange, but basically we're guaranteeing there's at least one x value where the derivative of that x value, that instantaneous rate of change, is equal to, if you guys remember this, f of b minus f of a over b minus a, the average rate of change. Okay, so the derivative or that instantaneous rate of change is equal to the average rate of change. Okay, one note for you, this value of c, just write yourself a note so you don't forget this. C cannot be an endpoint, so it has to be in between a and b, okay? So it can't be, a or b. So if it was from 0 to 1, this value of c couldn't be 0 or 1. All right, so just a note, that happens sometimes. And again, we're going to see this in different ways. One way you might see it is with a secant and tangent line. Okay, as you might remember, slope of a tangent line is f prime of c, right? Instantaneous derivative at a point, or instantaneous rate of change at a point. And slope of secant line is the slope between 2 points, aka the average rate of change. Okay, basically what this is saying is at some point these two lines are parallel, aka they have the same value, okay, at some value of c, some value of x, some value x equals c. So c is just another x value, right, that we're making up here. Okay, and just really important wording here. So slope of the secant will be equal to slope of the tangent. It could ask the question in that way. I could say when is, or what's a possible x value that the secant is parallel to the tangent line, or the slope of the secant will be equal to slope of the tangent. So just a heads up on that, as well as average rate of change equals instantaneous rate of change, right? This is a rock and right there, and f prime of c would be instantaneous rate of change. So just a heads up on all those pieces. Again, that's what it means. And the biggest thing you should get from this is right here, continuous and differentiable. Then we have this idea. F prime at some x value is equal to the average rate of change. Slope of the secant equal to the slope of the tangent at some point. So first thing you have to check is if something is continuous and differentiable between a and b. Notice for a and b, for continuous, it has to be including a and b. Differentiable, it's between. That's just something you should make sure you write carefully. A and b are brackets for continuous, and differentiable just has to be between a and b. Okay, so first we're going to verify that we can use the MVT, okay, and then we're going to see if there's a c value where this works to satisfy the conclusion of the mean value theorem. So we go from -1 to 1, okay, -1 to 1 for this function. This is just a random quadratic, right? If it's a polynomial, well then we know for sure, we just know what a polynomial looks like, right? This is some quadratic. There's no holes, there's no jumps or anything like that. So f of x is continuous on -1 to 1, and it's also differentiable. Differentiable on -1 to 1, that open interval, so we can use the MVT, right? So those are the two requirements. If you're wondering, how would you know when this doesn't satisfy one of the requirements, I'll give you a little counterexample here. What if I gave you guys, g of x is x plus 3 over x minus 2 on 0 to 5 or something like that. Okay, so can you use the MVT here? Well, it's discontinuous, right, at 2. Okay, it has a vertical asymptote at x equals 2, right? If we plugged it in, it'd be undefined. So since it's discontinuous at x equals 2, and 2 is in this interval 0 to 5, the mean value theorem doesn't apply. So we couldn't even use that for this problem. We would just stop and the mean value theorem wouldn't apply. So that's just a random thought for you. If you do see a problem that has something that's undefined or a piecewise function where it's not continuous or differentiable at a certain point in the interval, then we're going to have an issue. Okay, but since this one is, we can kind of continue on. Remember, the mean value theorem is saying, so we're using f of x, so it's saying f prime of c, okay, the derivative at c is equal to f of b minus f of a over b minus a. A and b are right here, -1 and 1. Okay, so let's show the work to the side here. The first thing you need is the derivative. So f prime of x would be 6x plus 2. Okay, so f prime of c, you can just replace it, 6c plus 2. All right, so that's this side. Okay, how about f of b minus f of a? Well, that would be f of 1 minus f of -1 over 1 minus -1. Okay, let's see what we get. If we plug in 1 here, we get 10. If we plug in -1 here, f of -1 would be 6, and divided by, this ends up being 2. 4 divided by 2 is 2. So the average rate of change from -1 to 1 is 2. Okay, so we set that equal. So again, just kind of show your work for each piece, right? So this answer is 2. I got that over here. And then this answer, f prime of c, you just find the derivative at c, 6c plus 2. We set them equal, and now we solve for c, right? If it did apply both conditions, or it did satisfy both conditions, sorry, we're going to find all the numbers c. So we're solving for c. 6c, if we subtract 2, is equal to 0. So your answer would be c equals 0. So at x equals 0, the slope of the tangent line and the slope of the secant line are the same. All right, let's try another one with a natural log in it. Okay, natural log, and again, by the way, we notice that c, I forgot to mention this, is on -1 to 1. So it has to be, your value that you end up with has to land within this interval, and it cannot be -1 or 1 itself. It has to be in between -1 and 1. All right. So like I said, let's try the next one. 2 natural log of x plus 3. Remember, the first thing you want to do is talk about if h of x is continuous and differentiable. Now, from -2 to 0, typically we can't plug in, like I couldn't have natural log of -2. That's undefined. But since we have this plus 3, if I plug in -2, I would get natural log of a positive number. If I plug in, -1, -1/2, and 0, all these things would actually keep this as natural log of a positive. So in this case, we checked that, okay, h of x is both continuous on -2 to 0, and it's also differentiable on the open interval -2 to 0, okay? So we can use the mean value theorem. That's basically what we're guaranteeing. Those two things have to be true. Again, I gave you an example up here for g of x. This is where some type of problem where you would not be able to use the mean value theorem at all. Okay, so let's try this out, guys. Remember, one is h prime of c, or the instantaneous rate of change at c, equal to the average rate of change between a and b. Okay, and we just do the scratch work on the side usually for each of these pieces. So h prime of c, okay, h prime of x, 2 would hang out. Derivative of natural log is 1 over whatever's inside times derivative of what's inside, which would just be 1, since derivative of x plus 3 is 1. So h prime of c would be 2 over c plus 3, if you just multiply the 2 into the numerator. So 2 over c plus 3 is equal to, switch colors here. In red, I'm going to do h of 0 minus h of -2 over 0 minus -2. Okay, let's see what we get. If we plug in 0 for, again, this original function, 2 times natural log of 0 plus 3 would be 2 natural log of 3. If I plugged in -2, that would be -2 plus 3, so 2 natural log of 1. And that's over 2. Okay, now natural log of 1, if you guys remember, natural log of 1 is 0. Okay, so you actually just end up with 2 natural log of 3 over 2. So you actually just get natural log of 3. Okay, so overall, this is equal to natural log of 3. And now we just solve. I mean, there's algebraically different ways to do this. You could multiply by c plus 3 or kind of think of cross multiplying here. So I get natural log of 3 times c plus 3 equals 2. Divide by natural log of 3. When does c plus 3 equal 2 over natural log of 3? Well, it's when we subtract 3. So c is equal to 2 over ln of 3 minus 3. Okay, and remember, this value should be within negative 2 to 0. If you do some calculations, it's like negative 1.1 something. So we're not going to calculate that right now, but just as a heads up, it is on negative 2 to 0. So this is a valid c value for this to work at. All right. So again, this value is where the slope of the tangent line is equal to the slope of the secant line, or instantaneous rate of change is equal to average rate of change for this function. If you're looking for that diagram, I think this is a helpful picture. That's what I mean when I say slope of secant between 2 points is equal to that slope of the tangent at a certain point. And we found that value c where that happens. All right, let's try, number 3, last one we're going to try here. So it says a test plane flies in a straight line with positive velocity v of t in miles per minute at t minutes, where v is differentiable. It also said it flies in a straight line, so we can assume it's continuous here. The plane is not just, off the map or something. So it's flying, it's differentiable, and then it says select values of velocity are given. Okay, based on the values, what's the smallest number of instances? So our answer is going to be, 5 or 3 or 1, whatever it may be. Acceleration of the plane could equal 0. Okay, so acceleration could equal 0. Well, I want you to think, how does acceleration relate to velocity? The derivative of velocity is acceleration, right? So if we're looking for something about the derivative, we're given v of t, just like when we're given f of x, we're looking for something about f prime. Okay, this is going to be using the mean value theorem. Now, the reason people get confused is a lot of times this problem looks a lot like what we did for intermediate value theorem. Okay, if I had a question about intermediate value theorem, I would have said something like, it would be showing or asking that velocity itself is equal to some number. So I would have said like, could we guarantee that velocity is 8 at some value of t? Here we're asking, could we guarantee that the derivative of velocity is some value? Okay, so that means we're using the mean value theorem. Intermediate value theorem, it would have said, can we guarantee velocity, or v of t is, 10 at some value of t? So we're going to use the mean value theorem. We checked the 2 conditions already. Okay, and so what we're looking for is this exact statement, v prime of t is v of b minus v of a over b minus a. I'm just going to put this is the same as a of t, just so we're not confused there. Okay, but it is the same exact statement we've been using this whole notes thing, whole notes page, which is the mean value theorem. Okay, that's what this is. And right here, we are wondering, when is this equal to 0? Okay, it says how many times would acceleration equal 0? All right, but we're given information about velocity, so we're going to use this table. If you set this fraction equal to 0 and you cross multiplied, basically it would just be when is v of b minus v of a equal to 0, because the denominator would be irrelevant. If you solved here, you would get when is v of b equal to v of a. aka when you subtract the 2 values, you get 0. So when are the 2 velocities equal? Well, if you look up here, you have 7 and 7. So if you were to do v of 15 minus v of 0, 7 minus 7 is 0. So your denominator would be 0. Numerator would be 0. Okay, if you did, let's see, what else do we have? V of 30 minus v of 25, I would get 0 again, because 2.4 minus 2.4 is 0. Okay, so there's 2 instances where this is true. Okay, so at least, where does this happen, guys? Where is acceleration equal to 0? At least twice, because v of 0 is equal to v of 15. That's what I did in red above. 7 is equal to 7. And v of 25 is equal to v of 30. Okay, and that would be it. again, what you're doing here is thinking if you plugged in, you know, v of 15, I'll show you really quickly on this one, over 15 minus 0, that would be 7 minus 7 over 15. 7 minus 7 over 15, which is 0 over 15, which is 0, which satisfies acceleration being equal to 0. So that's why we tried to figure out when are times that the velocity would be the same. All right, so that's another way of using mean value theorem with a table given. And again, the issue we're going to come up with and what we're going to keep practicing is when do we use intermediate value theorem, IVT, versus mean value theorem, MVT. Okay, think mean value theorem has to do with derivative. That's usually something that changes your idea of what to use. We're going to try number 4 together in class, so save that. And if you have any other questions, let me know. And thank you so much for watching.